Wait, why is this showing like that? Let's reconnect. There we go. Yes. Alrighty. Okay, so let's get everybody trickling in, and then we'll start. Alrighty, so today we're going to talk about relating those quantities that we talked about yesterday to each other. Good morning, Brittany. How are you? Okay, so we're actually going to talk about all of these in relation to pressure, how volume affects pressure, how temperature affects pressure, and how the moles affect pressure. But first, let's go ahead and put this in a non-chemistry kind of setting, and then we'll transfer that knowledge over. Alrighty, so situation for you. Let's say here's my house. Here's the door, chimney, blah, blah, blah. Okay, and here is my car. And here's me unloading a bag of groceries. Okay, yep. Hopefully, I hope the same thing. So we'll see how that goes. Alrighty, so I am gonna try and get these groceries into my kitchen. And to do that, I'm gonna walk into the house and drop off the groceries. And then I'm gonna go back and do it again until all the groceries are done. So let's say I am walking slowly with one bag of groceries at a time, and I've parked far from the house. Most of us would think this is rather inefficient, right? I'm kind of wasting a lot of time by doing this. So, how do we think we can make this process of getting the groceries to work a little better? How can I get those groceries into the house faster? Yeah, that's definitely one thing. Oh, definitely a good idea. What else could I do? Yeah. Yeah, exactly. Carry 5 bags at a time. Absolutely. One more way that we can get this to go a little faster. Recruit other people. Let's. Okay, that would work, but yeah, I wanted Lamonda's answer. So simply move faster. So instead of just, ambling along there, I could run, with my 5 bags and my closely parked car. I would get it over in no time. Okay. So we're going to see that these three are going to be actually related to this idea of pressure. So if we think of pressure, we're playing a very boring game of Pong here. So we have a ball that is moving in between two little thingies, and it's just getting bounced back and forth over and over and over again. That's essentially me going from the car with my groceries to the house. And so every time that particle of gas bonks into one of the walls and turns around, that's what pressure is. So every time a gas particle collides with something, that is what pressure is. So we saw that we could do 3 things to kind of change this. The first one that you guys said was to park closer. So if we think this gas particle is moving at the same rate, it's going to bonk into the walls more often, right? Because it's going to hit that wall on the right, turn around, go hit the wall on the left, turn around, go hit the wall on the right, forever. And that's going to happen more often than it did before, right? We could also say I'm bringing in groceries more quickly. The fewer trips that I have to take, that's higher pressure. That's what we're saying. And then as Brittany said, mom it, with 5 bags, you can kind of think about it that way too. You have high pressure that you don't accidentally trip and launch all your groceries all over the place. So, just think of it that way. So if we shorten the distance, which is the same thing as decreasing the volume, we are going to end up, the ball hits walls, it's going to hit those walls more often, and so that's going to be higher pressure, if we think about it that way. So moving my car closer to the house, decreasing that distance, will allow me to get groceries in faster. I will be able to go to the house, then to the car, then to the house, then to the car, in the same amount of time as it would have taken me one trip before. And so I'm hitting these walls, the house and the car, more frequently. And that means higher pressure. So mathematically, this is telling us that as volume goes down, pressure goes up. And vice versa. So if pressure goes down, volume goes up. The opposite thing. So this tells us mathematically, if we wanted to put this in an equation form. Wait a second, I seem to have frozen. Did I freeze for anyone else? Oh, I'm back. Okay. Weird. Okay, well, anyways, I couldn't see what I was writing. How interesting. So, pressure times volume is going to be constant. So that tells us if one of them goes down, the other one must go up, and vice versa. This is what is called an inverse relationship. So if we want to relate volume and pressure together, we have to understand that they act as opposites. So one goes up, the other goes down. We decreased the distance between the car and the house. we're able to get groceries into the house more frequently. Okay. Creature has grumbled in agreement, so that's a good thing. Or possibly disagreement, we never know. The second one we had was to carry more bags. So, if we go back to our original diagram, I don't know why these are all moving in the same direction, but they are. If we throw in a whole bunch of gas particles, something is going to hit the walls more often, right? Just putting more of them in there, we're going to have more collisions. So, more particles, it simply means more collisions. And so that's in our kitchen analogy there, that was bringing more bags. So the more bags we can bring in one trip, that means that we're going to get more bags to the kitchen more frequently. And so that's the idea here. If we put a whole bunch of balls in our little Pong game, we're going to be smacking them all the time. So we're going to be, bonking that first one, and then the second one will come, and the third one. All of these extra particles in there are going to hit those walls and then move backwards and hit the other wall, and so on and so forth. So this tells us that as N goes up, N is moles, I'll write that in a sec, pressure also goes up. Or conversely, if we take particles out, we'll have a lower pressure. So the more stuff we have in there, the more pressure we have. If you want to think about it again, like the more homework assignments I give you, the more pressure you have to get them all done, right? Something like that. So the more of whatever, in this case it'll be gas particles, the higher your pressure is going to be. And so this would be mathematically described in this manner. So if we increase pressure or moles, we have to increase the other one to maintain this relationship, right? Because if you think, 1/2 is 0.5, nothing crazy. Too much pressure, yes indeed. And if we increase the moles, that means that we have, I'm just throwing out random numbers here, but that means our pressure would also go up, right? So if we solve this, x is 2, right? It used to be 1, now it's 2. Moles used to be 2, now it's 4. They've both gone up proportionally. So, this is just like some random numbers, but that's how that... We're not ever going to use this equation as it is, but that's how we would. So whatever the constant happens to be, that's what you would do. So this all signifies what is called a direct relationship. So one goes up, the other goes up. One goes down, the other goes down. So these ones are kind of in sync with each other. Whereas pressure and volume were the opposite. We're going to see pressure in moles will be the same. They're going to want to increase or decrease at the same time, whichever one the other one does. Alrighty, last one was temperature. And so we're going to see here that we can relate temperature as well. So if we have this one that's moving sluggishly along versus this one that's zipping along, of course the one that's moving faster is going to hit the wall more frequently. Right? So frequency is, related to time, and time is related to speed. So, it's just going to bonk between those walls more often. So more pressure. And so we're going to see here that the temperature, why did I write that? If temperature goes up, pressure goes up too. Same thing. So this is also a direct relationship. And so we would describe this technically like this, mathematically. Whenever I write constant, it's just some number. I have no idea what the number would be. It's going to be different for, different gases and stuff, but it is just some number, whatever it is. And so your pressure and temperature for a particular sample will always be constant if you relate them together this way. Okay, so just how we can relate these three quantities to pressure. So if we saw that pressure times volume was constant, pressure over moles was constant, and pressure over temperature was constant. Those are kind of the three relationships that we've got come across here. And so, in fact, what we're able to do is combine all three of these together. And we're going to say that that's going to be an extremely powerful way to talk about gases. And so let's see what that would look like. So we know that pressure times volume is constant. We know that pressure over moles is constant. And we know that pressure over temperature is constant. And so we're going to be able to see this is a special constant called R. And this time, we know what R is. R is this lovely number, 0.08206. The units for this are liters times atmospheres divided by kelvins times moles. And if you ever forget your equation here, you can just make sure the units work out. If we have liters times atmospheres over kelvins times moles, that is telling us we have volume times pressure, temperature, and moles. All right, it's the same thing as above, just slightly, I guess they're reversed, but doesn't matter because multiplication allows for that. Okay, and this equals R. Oftentimes people will kind of arrange this alphabetically in one kind of line, and if you do that, if you were to move n and t onto the other side of the equation, you would get this. It does not matter. There's still the same equation, right? We've just done some algebra, tweaking it. This is what is known as the ideal gas law. And R is a universal gas constant. And it's always equal to that number up there. And we can use this law to actually calculate one of these quantities if we have the other three. So for example, Let me just write this question here. We'll see plenty of problems like this. Um, and like pretty much we're really only going to have 3 equations this chapter. You'll see a lot of them, but we really only ever use 3 of them. So the ideal gas law is probably the one you're going to use most often, and we're going to see this happening in other chapters as well. When we talk about reactions in the gas state, we're definitely going to be using this equation. So this question reads, how many moles of gas occupy 12.6 liters at a pressure of 2.89 atmospheres at 318 Kelvin? So if Brittany has not been kicked out due to lag, what do these quantities represent? What's that first number? 12.6 liters. What is that? Which of our letters for our ideal gas law is 12.6? Okay, it's possible she was kicked out or just had lag or something and she decided to watch it later. So that's a volume, right? Liters. Hey, awesome. Yeah, Lamonda, very good. Yeah, so that's a volume. We can tell because it has a unit of liters, right? We talked about yesterday about units of all of these quantities, so liters is always a unit of volume. Over here we have a pressure and a temperature. And so we're asking how many moles, which is N, right? So that's the one we're solving for. So all we have to do is plug this stuff in. So 2.89 atmospheres times 12.6 liters equals N times ideal gas or universal gas constant and our temperature. Yeah, awesome, Roger. So let's go ahead and look at our units. So atmospheres on the left side, atmospheres on the right side, cancel. Liters on the left side, liters on the right side, cancel. Kelvin on the top, Kelvin on the bottom. So we're going to be left with moles at the end of the day, which is what we're looking for, right? So technically we just have to do all this algebra. I'm going to do it real quick. So we had 2.89 times 12.6 divided by 0.08206 divided by 318. Oops. Oh, I didn't have numlock on. How silly. Sorry about that. 12.6 divided by 0.08206 divided by 318. Okay, so from this we get N is equal to 1.3954 moles. Okay, looking at sig figs, it looks like all of these numbers that were given have 3 sig figs, so we should go ahead and round that to 1.4 moles. One thing to note, the identity of the gas does not matter. So this could be oxygen gas, it could be nitrogen gas, it could be xenon, it could be neon, it could be helium, hydrogen, water vapor, sulfur hexafluoride, random gas of your choice, methane, who cares, ammonia. Any gas will behave the same way. All gases behave just like all other gases. So we're lucky for us, because there are no intermolecular forces here, the identity of your gas does not matter. So if this question had said moles of O2, or moles of NH3, or moles of CH4, who cares? Doesn't matter. For this type of calculation, the identity of the gas does not matter. As long as you have moles of it, you're good. Of course, if we wanted to convert that mole into something else, then the identity would matter. Like if we wanted to find out grams or something, then yes, that would matter. But otherwise, no. We're good. Okay, let's do another one. Let me put some sig figs there. We're going to have some unit troubles here. So problem 2. We're asking, what volume does 1.29 moles of ammonia occupy at 0 Celsius and 2014 torr? So, can we use these numbers right away? Can we use 1.29 moles right away? Of course we can. It's moles. Who cares? We're good. We have moles already. Can we use 0 Celsius right away? That one for sure not, right? Because we know that we have to have Kelvin. But we're still, if we tried to do that, if we tried to plug in 0 in here, we would just get nothing. And that would just completely ruin the point of doing this. So Kelvin can never be 0. So as a result, we're able to use it here. So for all our gas laws, we're going to see we must use Kelvin. And then torr also is not a unit that we can use right away, so we're going to have to mess with the units of this first. So let's mess with the temperature. If we remember, to go to Kelvin, we just have to add 273.15. So that tells us that this temperature is 273.15 Kelvin. Okay, cool. The pressure that we can't use is in torr. We have to remember that it's 760 torr for 1 atmosphere. That's our conversion factor that we introduced yesterday. Again, this is one you're going to be using pretty often, so it would not hurt to stick it in your memory, or maybe stick it on a post-it note and put that near your computer. So either way. This one I cannot do in my head. So 2014 divided by 760. That is 2.65 atmospheres. And I'm going to keep the 4 sig figs there. Remember that 760 is an exact number, so we are not going to worry about sig figs for our conversion factor. Okay, great. So we have enough information now. We're solving for volume, right? Oh dear, tablet froze. No, tablet, you can do it. Oh, okay, I'm definitely going to make sure we save this. That's good. Okay, tablet is back to normal. Maybe. Yeah, that's good. Okay, sorry about that. So, we're solving for volume, right? We could just solve our equation for volume first, if we wanted. Oh no, the second question. This one? Yeah. Just so you know, Ollie, you can always pause it or go back in time as well. I think there's probably a way to do that, but anyways. Okay, so there's our equation, thing for us. So I like to do it this way, where we set up our equation so that it already will solve for our variable. You're always welcome to do it the opposite way. If you just plug stuff up and then solve for v, that's totally okay as well. Does not matter. But the way that I will be kind of doing it, I like to use the right equation if we're solving for volume. Just makes it a little easier for me. Don't have to worry about what's on the top, what's on the bottom. Okay. Cool. So in that case, I'm just going to duplicate it. The moles was 1.29. I guess I'll be good and write my units. R, of course. Temperature was 273.15. Pressure was 2.650 atmospheres. Awesome. Okay, so let me plug and chug this real quick. 1.29 times 0.08206 times 273.15 divided by 2.65. And so the volume that I got doing this calculation was this number, 10.911. Looking at sig figs, we have 3, 5, and 4. We're going to not worry about our constant here. I guess we should, whatever. Here, 4. So we're going to need 3 sig figs there. Let me do my squiggly line. 10.9 liters. How did I know it was liters? Well, we're solving for volume, so that would tell me right away. But let's go ahead. We see atmospheres cancel, moles cancels, Kelvin cancels, we're left with liters. Okay, so this is just all you have to do is make sure everything's the right units, and then you can go ahead and throw it in your equation. Great. Any questions on that one? We're going to up the ante just a little bit. Okay, so how many grams of um 15-liter tank at 162 atmospheres, 25 degrees Celsius. Now we're sad because now we're asked for a quantity that is not explicitly in our equation. However, we do see that we do have 3 other quantities in this problem, right? We have a volume, we have a pressure, and we have a temperature. So with those 3, remember that the ideal gas law can be used to calculate the other one. So this is telling us, or we have enough information here rather, to figure out the moles. So if you're completely stumped on this, if you see something like this on the homework or whatever and you're stumped by it, do what you can with the information that you're given. That's always a good place to start. So with this, we don't have an n, so we should probably solve for that. So here's our gas law. So n is therefore PV over RT. Looks like the volume is okay, the pressure is okay, but the temperature we're going to need to adjust. So we're going to want to go ahead and add 273.15 to that to make sure that we get it in Kelvin. I'm not going to write that out because all you have to do is add that number, which we've done before, so we'll be okay there. Alrighty, so let's do it. So n is equal to, where is the pressure? 162 atmospheres times 15 liters. Gas constant, temperature. 162 times 15 divided by 0.08206 divided by 298.15. And doing this, you get 99.32 moles. Sig figs wise, it looks like we're going to need 3, so let's just remember that. However, this is moles. We're asked for grams. So we want to, this is just a unit conversion, so we're going from moles to grams. We know we have a conversion, right? That's molar mass. So for Cl2, that's 70.9. Just from the periodic table, take the atomic mass of chlorine, multiply by 2. So if we do that, 99.32 times 70.9 grams per mole. We do this times 70.9. We get 7,041 grams. And with the sig figs, it looks like we're going to have 3. So lucky us, we're going to need scientific notation here. No, we're not. We can just leave it as is. So with sig figs, we would get 70/40. All right, how was that one? We just had kind of one more step, which was to find the grams. And so in this case, we were able to use the other information given to solve for moles. And then just we remember that from way back when, we were able to convert grams into moles using the molar mass. Okay, any questions on that one? Just crying? Is it just because of the math? This math is easy. It's just algebra. Just multiplication and division. We can do it. Okay, so here's something for you. Good. That is my goal. So, this is really a goal on, catharsis and helping you to relieve your emotions by forcing you to cry. So, that's good. So, standard temperature and pressure is a set of conditions that people used in the 1600s when they actually did these sorts of experiments. Nobody does them anymore because they're boring. But way back when, this was defined as exactly 0 Celsius and exactly 1 atmosphere. So these would be a set of conditions that were considered standard, and for whatever reason, people still like to use STP in problems. So in case you go to some other place and they're using STP and want to make sure you know it. However, in like the 80s, this was changed to 0 degrees Celsius and 1 bar. However, even though that was 40 years ago, people still use the atmosphere one in their chemistry problems. Go figure. I really have no idea why. I guess nobody liked the change from atmospheres to bars, so they're like, no, I'm going to still use atmospheres. And so it's the way it is, unfortunately. So while this is the real definition, we don't use it. So I don't know why. Again, I mean, it's kind of pointless anyway, because nobody cares about this stuff. Because the experiments have all been done, and there's nothing really more to discover here. But this is what the one that we actually will be using would be the first one. Okay, and so this problem that we're going to do right now is something called molar volume, and it'll be important if you take 111. So, but we'll go through it. So, we have 0 degrees Celsius. We already saw that was 273.15 Kelvin. So we can go ahead and do this. So volume is nRT over P, which is 1 mole temperature was 273.15 over 1 atmosphere. You do this, you'll end up getting 22.4 liters. This is a special quantity because, well, it's kind of a passé quantity. Because we use 1 mole, you can actually use this as a conversion factor. So if you are at STP, 0 Celsius and 1 atmosphere, you can use this to very easily figure out the volume of 1 mole or something, or the volume of several moles of something, or the number of moles based on your volume. It's just a conversion factor. Notice that while I did say this was methane, it works for every gas. Remember that this does not, or the gas stuff does not care what your gas is. It could be nitrogen, it could be fluorine gas or something, or chlorine like we saw before. So this is basically showing us that we have 22.4 liters is going to be equivalent to 1 mole of a gas. That is how much 1 mole of gas occupies under standard conditions. And so, you might see something in the future like, what volume, that's a V, does 6.14 mole of at STP. And while yes, you could totally do your ideal gas law for this, you would always get the right answer. However, you can kind of save yourself a little bit of grief and just use this relationship that we just solved for. And so we would see in this case 6.14 times 22.4. This fluorine gas would occupy 138 liters. So this is not something that I like to ask as questions, but again, I don't know who your future chemistry instructors will be. So unless you take it at Saragossa, then it'll be me. But if you end up going somewhere else or whatever, or Bakersfield or whatever, you will probably see this again. So there you go. I have technically taught it to you. So so there we go. Alrighty. So that would be one conversion factor that, again, you could commit to memory, but I don't really think it's necessary. By the way, if you use the bar one, if you use 1 bar, you actually will get a slightly different number for this, because your pressure is different. It'll be slightly different. So just throwing that out there as well. Again, this is probably even less likely to ever come up, the 22.71, but there it is. Alrighty, how was that one? All right. Good. I'm glad. Alrighty. Did I just write PV over RT equals R? That was silly. There we go. So let's take a look at this. This is true for any gas at any conditions. So let's just call them condition 1. Guess what? Any other set of conditions would also equal R. Because this is true for any gas at any conditions. If we mess with them, we should still get our constant. That's why it is universal. And since R equals R, big maths, I know, that tells us that we can actually relate changes in these quantities. So the set of conditions for the first situation would still have to equal R, right? And since it would always equal R, we can set it equal to another set of conditions. And I'm just going to tell you right now, this moles one is actually pretty hard to change. Like, you would have to inject moles into the system, which is typically not something that's done. So this one is often kind of omitted. So you'll often see this equation instead as written this way. So this is going to be the second equation that we're going to work with in this chapter. This one is called the combined gas law. You don't need to memorize these names, but it is good if you know, it's somewhere in your brain that, oh yeah, okay, he's using that law this time. And this is going to be used this is when things are changing. So previously, the ideal gas law, wow, where did that go? Wow, this was a long time ago. Okay. There it is. This one is used for calculating one of the quantities when you're given the other three, or something that you can use to get to the other three. This law is used for when things are changing. So something that you would use this for would be, say, a gas at 1.94 atmospheres and 300 Kelvin is moved from a 0.62 liter tank to a 1 liter tank at the same temperature. And we would be asked, okay, so we see that we're changing something. We're changing the volume here. And so we're asked what the pressure is going to change as a result. And we're given a temperature that's not changing. But it could change, does not matter. Yes, again, you could just calculate the number of moles in the first conditions and then use that number to calculate the new pressure by doing the ideal gas law a second time, but I have a feeling you don't want to do that. So let's take a look at this. So again, this comes to kind of like digesting a word problem, right? We see that we have a pressure, a temperature, and a volume. So those would be our kind of initial conditions. And now, this other number is going to be our second volume. And we're told that the temperature is the same. So temperature 2 is also 300 Kelvin. So if you look here, we have 5 numbers we've come out of that thing. Our equation, lo and behold, has 6 variables. So we have 5 of them. We simply need to solve for the last one. So we're looking for our new pressure. By the way, it does not matter which one you designate as pressure 1, pressure 2, whatever, as long as you have them all grouped together. Like, those first 3 numbers all relate to the same, kind of time, and then we have a new set of conditions. So you can have named them all the opposite, but doesn't really matter. Okay, so P1, V1, T1 equals P2, V2, T2. If we're solving for P2, we can solve our equation for that. I've just moved v and t to the other side. I've multiplied by the reciprocal of those two. So just algebraic manipulation. You do not have to do that. You could just plug in your numbers and then solve after. That would totally work. But I typically like to, just personal preference, I like to solve the equation first. So pressure 1 was 1.94 atmospheres. Volume 1 was 0.62 liters. Temperature 2 was 300 Kelvin. Temperature 1 was 300 Kelvin. And volume 2, I think, was 1 liter. So notice liters cancels, and in fact our entire temperature will cancel. We don't even have to worry about temperatures, and it's not changing. Who cares? Forget about it. We can do this math. 1.94 times 0.62. Don't need red right now. If we do that, we end up getting, it looks like we're just going to have 2 sig figs, so 1.2 atmospheres. Note the unit is the same as what it used to be. So let me explain that. Your units can be whatever you want for pressure and volume, as long as they're the same. So you can have pressure 1 in millimeters of mercury. That means you're going to get pressure 2 out as millimeters of mercury. Does not matter what your units are, as long as they are the same. So as long as your volumes are in the same unit, your pressures are in the same unit, use whatever units you like. Does not matter. You'll get the right answer. Your temperature, of course, must be Kelvin. Because if you have 0 degrees Celsius again, that's going to mess stuff up. Not a good thing. Actually, I'm going to write that in angry red, just to remind you. Temperature must be in Kelvin. Okay, so tomorrow, or I guess we're not tomorrow. Hooray, it's our Friday. Monday, we're going to continue this stuff. So I'm not going to give you homework on gas laws quite yet, because you have plenty of homework for intermolecular forces. Just to put it out there, you might be scared that there's a whole bunch of big molecules and carbon-containing things on that homework. Trust me, there's nothing new there. This is all material that you will be able to solve. And the questions are designed to kind of like help you to apply the concept of intermolecular forces into kind of like a new situation. So this is intentional. It's not meant to scare you, but it's to help you show that these intermolecular forces have big ramifications in terms of physical properties. And so like why certain things will dissolve together or why they'll interact in a certain way. It's mostly, most molecules in the universe are, just in terms of like how many there are, most of them are organic molecules that have these sorts of hydrogen bonding things going on. So that's why it's kind of framed in that light. Alrighty, so with that, we are out of time for today. So I will see you all on Monday. Have a lovely weekend. Enjoy your homework. It is 11 pages, but again, that should not scare you. It should be easily doable in, like 2 hours or 3 hours or so, which is pretty standard for, a week of chemistry. So, homework. So don't be daunted. Some of the pages are just filled with, it'll be Sunday night. Just a reminder, I did send out an email. Your exam is not on Monday. All right. Chem 111 has an exam on Monday. You guys do not. Your exam will be the week after, which will be on the 20th. Let's have a look. 26th. Yeah. Okay. So I did send that in an email. Don't be scared. We will come back and do more gas stuff on Monday. All right. So take care, everyone. Bye-bye.